Okay. Hi, everybody. This is episode number 6 of the Physics of Bitcoin. We meet every Wednesday. It is my time, 7:15 Pacific Standard Time. Stephen is in Thailand, right? What is the time over there?
It's Thursday morning, and we're 10 o'clock in the morning here. So
Actually, another day. So.
yeah.
We basically, for the people that are not familiar with our show and they are just joining, it's a show where we go a little bit deeper in understanding Bitcoin, in particular from the angle of using physics, because both myself and Stephen, we have a PhD in astrophysics, not just in physics, but astrophysics. And Bitcoin is supposed to be a black hole, of some kind. So it's actually a pretty good specialization. And we talk about indicators, different approaches, different ideas. Where having a physics angle maybe can help to go a little bit deeper in understanding what is going on with Bitcoin. And so we cover different topics today. In fact, maybe. Stephen can talk about the agenda today. He has several things he wants to talk about. I will cover other topics, but go ahead, Stephen, and talk about
Yes.
what we're going to talk today.
Yeah, great to be here. It's been 2 weeks. We weren't able to have it last week. I think you were on the road, Gio, and but nice to be back with the group. And I will I'll put up the slides. I have a few slides to show. So can you see those?
Yeah, we see them.
Okay, great. All right, let me go into full screen mode. So I think it's January 22nd there and January 23rd here. So there's duality in 2 phases already, just in our dates.
Yeah. By the way, that symbol is the symbol of my city, Genova. It comes from Janus. Yeah.
Oh, that's the city of Genoa, huh?
Yeah, the city of Genoa comes from Janus. I recognize him, right? The god of 2 faces. Yeah.
Well, I'm born in January, and Janus, of course, is the Roman god for which January name comes from and the month that we're in. And as people know, 2 faces, so we can see what's going on. And so the commonality here is the 2 faces shown in this statue of the Roman god Janus, and the 2-phase nature of Bitcoin. And those 2 phases are a core power law behavior, and then bubble phases, or phases where it gets very volatile and has actually exponential and even super exponential rises and declines. So that's what we want to talk about. Here's some agenda. First of all, physics of Bitcoin. Bitcoin is rooted in physics. So we're going to talk about just the energy aspect of it. One little interesting historical note there. I'm going to mention in passing that Bitcoin is anti-fragile. We're going to cover again, because it comes up all the time, the difference between exponentials and power laws. And it's both relevant to the content here, but it's relevant more broadly as people, talk about things like, will we see $1 million Bitcoin in 2025? We say no, because, we understand that we have a core power law behavior. We understand there's some exponential behavior, some volatile behavior on top of that, but it does have limits. And we'll show what some of those limits are. And so we'll look at both Bitcoin denominated in dollars and Bitcoin denominated in gold ounces. So we've got quantile regressions. It doesn't matter too much for this discussion whether you use an ordinary least square or whether you use a quantile regression. You get the same general behavior, and you can see that they're two phases in how Bitcoin progresses. And what you do is you look at the residuals after subtracting out these power law behavior. For dollars, where Bitcoin price in dollars, where we've already entered the red zone, which is what I call, the volatile phase. You could call it, use whatever color coding you want, but for now we're saying red zone. And I will show for gold as well, and you'll see a somewhat different status for that one. And then I'm going to make an analogy related to fluids, because fluids have both turbulent and non-turbulent behavior, what we call laminar flow, as more steady flow. And then even an analogy between yin and yang, which are like the two faces of Janus that you have in Roman mythology. Well, in Eastern mythology, they have a yin and yang, a duality. So this is a tweet that I put out, I don't know, I think while I was off at the beach a few days ago, probably 2 or 3 days ago. And I had seen this other tweet that somebody had put out about Buckminster Fuller's prediction. He was a very famous thinker, philosopher, architect, quite a didact. He covered many areas. But in 1967, so how long ago that? That's 60 years ago, nearly. Buckminster Fuller said, by the year 2000, there will be a realistic scientific accounting system. Wealth is energy. Wealth always increases. So he was only off by 9 years. It was announced 8 years after, and it was put into progression at the beginning of 2009. And I state that it's the first completely scientific standard ledger and the first direct from energy monetary system for enumerating wealth, and that it appeared 42 years, nice number, after Fuller's prescient statement. And what we have is unbounded energy that we're putting into absolutely finite Bitcoin. Lots of energy into a capped monetary system is superior to little energy into an exponentially growing money supply. So this is the power that underlies the power laws. That is the power that's behind proof of work. Energy, as we know, is power times time. And the amount of energy that's being consumed right now by the millions of computers of the, specially designed ASIC variety that are, as we speak, mining and minting Bitcoin is about 19 gigawatts. And every block, 600-second block, it transforms that, at a rate of 800 exahashes per second of calculation that are needed to solve the block. So that's it's about 3 terawatt hours per block. The next slide, this I was going to show last week. It was slightly more relevant last week, but it still shows the point. This is some price behavior from last week over a 4-day window. And you may remember that we dropped almost back down to $90,000. And then we quickly went up by 10%. And we were back at 99K. And then since then, we've pierced 100K again, retested 100K, gone back up to set new highs, and now settled back to about 102, 103,000. But Bitcoin always bounces back. It's been anti-fragile for 16 years. And that's because of this underlying nature that it has of the network effect that it's built, and a network that's founded in energy that produces it. Now, for exponential or power law, I wanted to show this slide, which is the history of the return for each of the last 4 completed epochs. So epoch 1 that, ran from 2009 into 2012 with the first halving, and then 2016, 2020, and then up until the last halving, which was the 4th epoch that closed in April of last year. And the orange line is the average return per month in that epoch. So in the first epoch, 30% average return. In the second, 15%. In the third, about 10%. And in the fourth, about 7% or so. So it's steadily come down. And this is completely consistent with the power law. And it is also monotonically decreased in terms of volatility. So the blue line shows the volatility, which is just the standard deviation for all these 48 monthly returns that you have in each of these epochs. And in the current epoch, we're running a bit higher. We're more like 10% per month because we're in the favorable part of the cycle right now. But we'll see how it settles out for the full epoch. And I expect that the volatility will also be somewhat lower for this latest epoch, epoch 5. Now, if you had exponential behavior for Bitcoin, these lines would be straight. They would be constant compound annual growth lines. And they're both clearly not straight. And they in fact, are consistent with power law behavior. Okay, so into some regression and the two-phase behavior. This is Bitcoin dollar versus dollar data. It's weekly data. This is a quantile regression, that's up to date with 9 quantile levels. It has over 750 weeks of data. And my point with this slide is, with these 9 levels that are somewhat equally spaced, but not exactly so, but we're already seeing indication of the two-phase behavior. And that is because the lower quantile levels are all bunching up. In fact, the 3 lowest levels at 0.05, 0.1, and 0.2 are almost on top of each other. And then we have the 0.4 and the 0.5 levels in the red and the purple. And those are close to the lowest ones. So these first 5 are pretty much bunched up. And then the next 4 are quite spread out, where we have a lot more volatility, and they're reflecting, the structure of the peaks and how high those peaks go. They're also reflecting some convergence of the lines as the peaks come down in their heights from one to the next. But we're already seeing some indication here of the two-phase behavior with a lot more space above the median line, which is this purple line, the 0.5 quantile. About 2/3 of this sort of space or width of these lines is above that. Okay, the next slide makes it much more clear. So here we've subtracted out the median, which is the 0.5 quantile, and we're only showing the residuals with respect to the core power law, and that power law is about a 5.8 power of the age. And so what you see here is the dots are the log residuals. So if the residual is at 1.0, that's a factor of 10. And if it's at 0.5, that's a factor of 3 above the median value from the quantile regression. Now, I've somewhat arbitrarily divided them into the top 40%, the bottom 40%, and the middle 20%, and color-coded them as red for the top and green for the bottom and yellow for the mid-range. And what we can see is we can observe a few things. One is that the transitions from the green zones to the red zones are pretty sharp.
Right.
It spends just a little bit of time in the yellow zone, and once it gets into the yellow zone, it kind of goes straight up into the red zone. Mm-hmm. And then if it's falling back, it drops from the red zone back into the yellow zone. And we only get very few kind of fake outs where you go up into the yellow zone, but you don't completely traverse into the red zone. We have a couple of those. Maybe you could argue 3 of those. But in most instances, it's a pretty clear transition, a rather sharp transition between the core underlying power law that these green dots and the green shaded regions represent, and the red dots and the red shaded regions represent. So in addition to the individual observations, I've taken a moving average, and that's a red line and a green line respectively. And I used a 26-week window, half a year window for the moving average. So you can see how that traces out and traces through roughly where the strongest bubbles are. And then these color-coded bands in the softer red and softer green colors are the plus and minus 1 standard deviation bands for either the red zone or the green zone.
All right.
And what we observe here is that the width plus and minus 1 standard deviation residual uncertainty for the red zone is about 3 times as high. It's about 2.8 times as high as it is in the green zone. So we have this sort of stable core power law, which in fluid flow analogy terms would be laminar or steady kind of flow. And then we have these turbulent regions that are color-coded in red, and those are our bubbles, exponential up, exponential down, back to the power law support with transitions around the mid-range, these yellow zones. If we look at the very final data points, and there's a big red arrow, it shows that we are just now entering the red zone if you use this sort of division.
All right.
Now you could have divided it 1/3, 1/3, 1/3, and you'd see something roughly similar. But because the transitions were so sharp, I chose these kind of sorting values. Okay, so the next slide is in gold terms, Bitcoin measured in gold. And I used weekly data. I had daily data. I weekly averaged it so it'd be comparable. And here we show the quantiles in the lower portion, the lower left of the slide. This has 7 quantiles, not 9. But you see the same bunching up, below the red line, which is the median quantile, 0.5. Things are bunched up. And you see that the data really hugs, those bottom 2 or 3 quantile levels before, heading up into a more volatile or bubble region. So this is weekly average data, daily data, and 5.5 power law. And so you see a similar chart here. You see the same behavior. You see the rapid transitions from the green to the red zone. You see only a few false breakouts. I see maybe 2 or 3 here. And then you see the width, again, in the red zone of the plus minus 1 standard deviation. The volatility is, again, about 3 times as large.
Mm-hmm.
And finally, at the very end, you see that we have not yet entered the red zone in gold terms. We're still in this yellow mid zone. In fact, we're right around the quantile prediction. The fair value is around 40 ounces. We're just below 40 ounces. Mm. And to get up into the red zone, we would need to be at about 50 ounces. So a couple of points. One is there's a lot of headroom here for Bitcoin to rise in terms of gold during 2025. And as it does so, as we expect it to do so, it will serve as confirmation for the chart that's a Bitcoin dollar chart. Any thoughts or questions on that?
You do it slightly differently from me. In fact, in a moment that we can show also my explorations of this topic. Mostly because you are not normalizing by the volatility, right? You allow for the volatility to express itself as this decay of peaks, right? You didn't do any normalization of the volatility.
Correct. I did do it. I have a chart that has it. And, if you normalize it to both sides, so that it's plus 100 to minus 100, going minus 100 for the green side, then it looks a lot more volatile. But then your eye is also misleading you a bit because that's a much lower volatility in the green region.
Right.
But if you want to build an
indicator, I did it in that way to compare them, easily. But it's different way of, like, it's always good to do it in different ways because you gain certain insights by do it in different way. One thing I'm wondering, if you go to the previous slide, if you don't mind. Now, these green dots, they seem to be much more aligned, right? Suggesting there is a real stable flow that roughly seems like about around maybe minus 0.1 residuals, right? And then if you go to the gold, it's still kind of in the same region, but there is a little bit more variability. You understand why that is so, or is it?
No, I think gold,
meaningful?
has outperformed the dollar, obviously, right? And
Yeah.
so our power law is lower by about 0.3. So instead of
I
a
see.
5.8, we have a 5.5.
Right.
But a lot of that outperformance was earlier on. So it's noisy in the
I
first
see.
several years.
I get it.
Yeah.
Now, and in general, right, the way I interpret all these is really is almost like there are two power laws, right? There is one power law that is the stable power law that is below the reference line, and then there is another one with added volatility. At least that is one of my interpretations.
Mhm.
That we are still moving in a parallel fashion. We are still growing with the power law, but then the bubble can be understood as power law plus additional volatility, and this is why you have these large bubbles. Is that your interpretation?
Yes, that's right. I agree. And now that I'm back, I'll show the next slide. Here's the histogram of the residuals, and I know you've looked at this also. Now, you can do this for the dollar. You can do this for Bitcoin relative to gold. It's a little more obvious when you do it Bitcoin to gold that you have two peaks.
Yeah.
And it's very obvious on this one. It's pretty obvious on the other. And so one peak corresponds to this bubble territory. And if you look at the left peak of this histogram, which is just showing, in x-axis, you have the residuals, right? And it's interesting first to note that the smallest residual is down around minus 0.5. So we've got this strong floor. In fact, you don't drop much below minus 0.4.
Right.
But you can go all the way up to 1, at least historically you did, or more. And so we've got this clearly very skewed overall distribution with a long right tail. But within that, we seem to have something that looks like a Gaussian or a log normal that's slightly below 0, right? That would be the lower quantiles in the regression, so the core power law.
Yeah.
And then we have something, that maybe you can model with another Gaussian that's wider for the bubble territory.
Yeah.
Now that I'm back, I want to play with this and do some modeling. I know you've done some
yeah, we
yourself.
need to go deeper because there are a lot of consequences. One is many times people criticize the Bitcoin power law model saying, oh, your residuals are not Gaussian, right? That is one of the expectations when you have a decent model that can be represented by a regression, by a least square regression. And my answer is exactly this: say, no, it's actually you don't realize there are two signals. There is the general power law, and then there are these oscillations. And actually, if you think it as two Gaussians, now you do recover that good behavior that you are expecting. It's just that it's a little bit more complex, and you have to consider this. But it's still behaving very well because if you focus only on the data below the power, the general trend and above, then you recover that nice behavior. That is one of the possible consequences. That it's actually an answer to this criticism. And the other is that there is the power law is always there, right? And the way to interpret the bubble behavior is just what I said before. That I think actually that one is more like kind of probably log normal. And so if you will take the log of a distribution, now you will get a normal distribution. That the way to understand the bubble is nothing else than the continuation of the power law behavior, but now with additional volatility. And this is why you can have very large deviations, because it's possible, right? You can still go 2 standard deviations away and get very large deviations. So the interpretation, like many times, right? I will not mention names. British Hodl. He will say, "Oh, what is the good of a model that tells you that the price can go from 10,000 to 150,000?" But that is not what the power law says. It says we need to watch at where we are in the cycle, because according to that, right, you will have to switch. This overall distribution. It's true that is the overall distribution, but because it's bimodal, you kind of apply the one that it's pertinent to the particular situation. So when you are in this time when we are not in a bubble, then you switch to the one on the left. Is in a sense, I suggest you to kind of color code it in a sense, right? Color code the different bars. So it's clear that is seasonal, right? That we switch between one and the other. So make one red and the other one, the particular bar, because that can also be calculated. When do they appear, right? You can color code the ones that are relevant when we are in one mode to the other ones, right? There's really two superimposing, slightly overlapping distribution. Do you agree with that?
Yes. And, this shift in volatility regimes is not unique to Bitcoin. This happens in financial markets a lot,
Exactly.
so you can have the S&P behaving with low volatility, and then it can shift into high volatility and then even higher volatility. Now, as it turns out, high volatility in the S&P tends to be more associated with crashes. For us, high volatility is associated with, nice right tail positive convex skew, very very agreeable to us, but then followed by crashes, back to the support.
Strong corrections. Yeah.
But what we have is a much more steeply growing underlying trend. It's not growing at 10%; it's growing at 40% underlying trend.
And again, this shows how powerful the framework of the power law is, because this very nice bimodal behavior is highlighted by dividing things through the power law, using the power law as a reference. All of a sudden, you see this very organized, beautiful pattern that you will not be able to, derive unless you add this framework of the power law. You agree with that, right?
Yeah.
It gives us
So, getting to a certain price is a path-dependent process, right? You don't go from 100,000 to 500,000 overnight.
Yeah, exactly.
You've got to go into the bubble and see how far the bubble goes, and it may take you up, 2 sigma relative to the overall mean or median power law trend.
Yeah, this is why until we have evidence that maybe we don't have bubbles anymore, that I think it's unlikely, because there are a lot of first principle reasons why we should have this kind of oscillation. Maybe they became smaller over time, but they should be there. But until we have evidence of that, I think this should be the way to understand Bitcoin, that there are these two modes and we oscillation. And, and the idea of creating some kind of upper channel, that is some of the analysts are chasing that idea, right? That maybe there is some kind of useful or meaningful upper channel. It's something that you can do, but it should be taken with a grain of salt, because and this with what we said in the previous episode, right, when we were discussing the quantile. Like, you have an example here on the left of a quantile model where you have these lines in that region when we are close to the bottom. It will be wrong to think that if that top quantile is a 90% quantile, that there is, about 10% chance that you can go above it, right? Because when you are close to a bottom, the probability, even if you can draw that line, that 90% quantile or whatever that is, right? It's the 95% quantile. The 95% quantile, it doesn't mean that there is a 5%. It will be the wrong interpretation that there is a 5% chance during the time that we go above that, right? Is that correct?
Well, it's 5% or 10% over the whole life, but it only happens when you're in these extended bubbles.
Exactly. So sure, you can continue to draw that line, but it loses a little bit of meaning in these regions where it's almost impossible to arrive here, right? It will not be the correct interpretation of these upper channels, so you cannot really. So if the idea of creating these upper channels is to be agnostic to the oscillations of Bitcoin, to the seasonality of Bitcoin, is kind of really failing in doing that, right? This upper channel. That is my position. But it's still good to think about that. You have this seasonality, and they should be accounted, because otherwise you will get an incorrect picture of what Bitcoin is doing. Do you agree with that?
Yeah, I mean, my attitude is we have evidence for quasi-periodic bubbles. We don't know exactly the cause nor exactly what the period is, but roughly 4 years. In the past, people talked about halvings a lot. Halvings can happen for various reasons, in the sense that it could just be a psychological phenomenon as well, right?
Mm-hmm.
So it could be a
I agree
market
with
psychology phenomena. So you could, even though the halvings are less important in terms of coin emission, is now very small compared to how much Michael Saylor buys, there's still some market psychology associated with that.
Yeah.
Then you have what is clearly pretty important, is the liquidity. And Michael Howell has shown that their dependence on liquidity is very strong. It's roughly a power law of the 10th power in terms of Bitcoin price relative to his liquidity index. Now, his liquidity index, it doesn't go over many orders of magnitude. It goes over about 1 order of magnitude in, I think, natural log terms, in fact. So it was only like 1 factor of E. So we'll see how well that persists. But the relationship's pretty strong. And we do know that, Bitcoin is correlated to the stock market and to tech stocks, and those are driven by liquidity.
Right.
And, people need to have money to buy this stuff. And there are a lot of people that are trading that are not hodlers, so there are a lot of factors.
Yeah.
And then, of course, there's FOMO. Once a bubble develops, it's going to continue to go higher for at least some period of time.
Yeah. And I'm glad that you reproduce or expand on my result, because these are some of my slides that I already show, but just to kind of compare with what you already did, because we are talking about this topic, so I think it's relevant. So this is what I did. I calculated this deviation. So these are pure deviations. They are in percentile. So basically, is price minus the trend, the power law trend, divided by the trend. So it's not quantile, but based on percentile differences between the overall trend given by the regression. So it's different ways, and it's nice to see convergence, when you do different ways. And what you see, it's a
very sharp transitions, right?
Right, very sharp transition. And you can already identify 2 regions, right? And it turns out, by the way, the 54% of the time we are in this lower region. So, and what I did here, I play this game because, Plan C, for example, is repeating that this quantile model is supposed to get away from the cycle, but I don't agree. I strongly don't agree. And so I've kind of taken at face value his claim, and I randomize the order of a dot. So you don't see the cycles here because I simply scramble them around. And they did that to show, look, even when you scramble around, so you're really taking seriously the idea that we don't have a pattern, we don't have an oscillation, you still see in an indirect way that there are 2 modes, because sine waves or sinusoidal waves, or quasi-periodic behaviors can be understood as bimodal, right? You have most of it, we know, being physicists, that basically most of the time in a sine wave you spend it at the top and at the bottom, and very little in the middle, right? That can be demonstrated quite easily. So you can see already by the distribution of it, even from a statistical point of view, that we are dealing with a bimodal phenomena. Even when you take it seriously, that you don't want to look at the cycles, and you don't want to be distracted. So it was a way of not being distracted by the pattern, right? And still the distribution is there, showing that there are 2 modes. Now, it's even more striking if now you actually divide it by the volatility. If now you correct by the volatility, and I show you the next slide. So here I did, instead of dividing by the trend, right, take the price minus the trend, and now I divided. You can do it by the volatility or by the price itself. And now the two modes are even more clear, right? And and in fact, they are very similar in behavior, right? They have this difference. Basically, there is this clustering of data points around these red lines that represent actually the average of these points, and you can see that there is no basically once you correct by the price of the volatility, you basically explain why we had large bubbles in the beginning and now we have smaller one, because basically is an artifact of the volatility itself that is gone once you correct for it. And so basically it's the same behavior. Bitcoin has behaved exactly the same from the beginning if you can correct it, if you can correct by volatility. And this is the distribution that I get, that is kind of similar to yours, but now, the two peaks seems a little bit more similar because of that, right? Because I normalize by volatility. So they are much more similar in that sense. They are adjusted by that volatility factor, and this is why they look almost Gaussian, both of them in that case. And this is the strongest response to whoever says, oh, when you're taking residuals of your power law, you don't get a Gaussian. Well, I get two Gaussian when you do it correctly, and you see what is going on. It's a more complex system than what it appears in the beginning. But I think this idea of separating the two modes and getting proper statistics for the two modes, it's the right approach. It really shows, it simplifies the behavior, but at the same time, it shows that it's a little bit more complex than just a fuzzy power law, right? There are precise oscillations. So it's really cool. I think we are doing a lot of progress. There is probably more information to and go deeper in this. What do you have in mind? How will you like to explore next?
Well, I just wanted to. I want to analyze these histograms with a couple of different methods, and see what kind of shapes are fit to them. Whether it's two Gaussians or a Gaussian and some other shape with a longer tail. Yeah,
that is a
so
good,
that's the next step for me. I've just got two more slides if you want that are
absolutely
analogous,
please
and
go ahead.
Then I can close out.
Yeah, please go ahead.
So this is an analogy with fluid flow, and this is fluid flow that we all care about. It's the blood flow in the aorta.
We don't see your slides.
Maybe you need to put me back up because I am sharing.
I usually see.
Let me stop sharing and then I'll restart sharing.
Retry. Yes.
How about now?
We get
okay.
Okay, here it is.
Okay, so an analogy between that behavior and fluid behavior. And I stumbled on this. This is, blood flow in the heart, and in particular, in your cardiovascular system as a whole. It can be both laminar and turbulent. Laminar, more steady state; turbulent, more like these bubbles. And in fact, with every heartbeat, there's a transition between laminar and turbulent, certainly in the large vessels. And particularly, this is a report from Nature Research about the behavior of the blood flow in the aorta. And in fact, it turns out that something that we call the Reynolds number, which is the division with, when you transition from laminar flow to turbulent flow, it's what fluid physicists use, that can be inherited. And they find that there's a 40% heritability of this Reynolds number in the population that they tested, which had over 1,000 subjects in the UK. Now, for this aorta, which is, of course, your biggest vessel, leaving the heart, this quantity that we call Reynolds number, which measures the propensity to turbulence, depends on the density of the blood. It depends on how fast it's flowing, the velocity. It depends on the distance that it has to flow. This aorta is kind of U-shaped, so there's a there's a length associated with that. And then the viscosity, the thickness. It turns out density and viscosity don't vary too much. But the velocity depends on the width of this tube, right? This aorta tube. So if you have a wider aorta, it doesn't have to flow quite as fast. And, so you have a lower Reynolds number. And then the distance is another factor. If the Reynolds number is high and you have more turbulence, you can imagine that there can be more chronic damage to the vessel wall. And that's why they were investigating this. And they found indeed that, there's a significant inheritance associated. And that's just kind of details here, but really it's about this analogy between laminar flow and turbulent flow that you have happening, inside your body with every heartbeat. So we have sort of this heartbeat for Bitcoin, but it has, instead of, once per second, it's kind of a 4-year heartbeat that we have.
I like it. It's a beautiful analogy.
It's going through this same transition from the laminar flow to the transition state, which would be our yellow, to the turbulent state. Every heartbeat, or for us, every cycle with Bitcoin. So there's some sort of natural rhythm. So that's one analogy. And I'll close with this yin and yang. I just kind of put the question, I just had that thought come to mind, and I put the question to ChatGPT, and it agreed. It said that the core power law growth is the yang. That represents activity, growth, structure, sustainability. And it aligns with the long-term adoption, the network effects, the utility, the foundational steady progress of Bitcoin's growth over time. And then the yin is chaos, volatility, speculative, emotional, and disruptive phases with exuberance, over-exuberance, correction, and rebalancing. So I thought that was kind of fun anyway, if not interesting as well.
It's beautiful. I love it.
I will take my slides down now. Okay.
And so I want to show two things next. First, I actually want to show you, I already showed it last time, but this is my realization on TradingView of all this knowledge. Basically identify the two regions. Now you can do it in more complex ways, but sometimes it's an overkill. For example, in theory, I use a hidden Markov method here, to identify the two regions, but it's not necessary. It's really what is fundamental is to divide the two regions in terms of above and below the power law given by the normal regression, the least square regression that we usually use. It's good enough. What is missing is identifying the transition regions. That is important, and I will do that next. But basically, the two dark lines below and above are these averages. So basically, I took only the data points above the reference line, only the data point below the reference line. Then I did basically a cumulative sum and the kind of cumulative average, right, over time. And it becomes more and more stable as you go in time, right? And this is why it looks pretty straight even for the upper region where you have this huge volatility. And that kind of supports my intuition that really, even when we have a bubble, the power law is still there, right? It's part of why it kind of looks almost mysterious why we leave a power law, right? Probably the strongest power law is the support line, the white line. Then after the bubble, we go back to it, right? We have done this over and over again. It's simply because we never leave a power law, visually looks like we are leaving the power law, but the power law is still there. So that is what I want to, kind of strongly demonstrate that is the case. But right now, this is what my intuition tells me, that we are still moving along the power law. The process is there. It's just that the bubbles are identified by larger volatility. And this is why it looks like there is a second, there are two power laws, one below, one above. And in addition, because of what these shaded regions show, is the volatility. And you can see kind of log normal, right? Because it's not symmetric. Remember here I'm using deviations that are normalized to volatility. So that log normal behavior is more evident. And so it looks like it's rare that we go below the support line, the middle line, right? The reference line, even when you add a volatility, because there is more volatility towards above than below the middle line. And I don't know if I am correct in this interpretation, but the way to explain why we have this peak is nothing else than say, at a point, we will have so large volatility that actually the bubbles allow for these peaks, because it's nothing else than the average behavior plus 2 standard deviation above that. And because these standard deviations are large in this region, we can account for these peaks. Basically, by the time the price goes in this darker region that correspond to 2 standard deviations, then it's time for the price to correct. And this is why, the price starts to go down, because it's too large of a deviation. So that is my interpretation of this. So it's pretty nice to see it all come together in a single indicator, right? That has this bimodal behavior. Do you have any questions or comments?
No, it looks like you're getting two kinds of mean reversion. There's a mean reversion within the red zone.
Right.
And then there's a mean reversion back down to the green zone.
Correct. Yes.
Yeah.
And when you are in the green zone, for example, this is how you can explain the bottoms, because you say, okay, we are deviating too much from what is supposed to be, if you want to call it the real power law, that is this dark green line. And so it needs to be corrected. It is going to correct itself and is going back to that green line. And same thing when you have a deviation that is too far upwards, like we had, for example, in March, right? And probably all this was due to the excitement due to the ETFs. The price deviated. It kind of touched the reference line. We don't spend a lot of time there, right? And then because it was too much on the other direction, it was not the right time, to cross, because the right time it happened just recently in November, right? When we are supposed to cross this, in a steady fashion, right? We are going to stay there for a long time, for almost 2 years. We are supposed to stay above the reference line for almost 2 years, at least. This is what happened in the past, and not just temporarily. It was not supposed to be there in March, and so the price corrected and it went back to that green line. And again, for all the people that say the power law is not precise, they don't know what they are talking about, because now, once you understand it in terms of this bimodal behavior, you can see that the price is very clustered around these two lines, the red one and the green one. It's very contained. I don't know how precise it could be, given we're talking about the behavior over 8 order of magnitude and something that is very volatile like Bitcoin. So once you understand it in that way, actually, it's a pretty narrow region of variation, right? Deviations from this trend. It will be very wrong to think at any time the price of Bitcoin can go anywhere from the support line to the to top deviation. That is not the right interpretation. The right interpretation is that given the particular mode that you are in, we are around these green bubbles, right? That you can look at recent. So in these particular indicator, you can actually play with the parameters. So for example, right now I'm using 250 days for the standard deviation window. You can make it smaller, and it will be able to actually track better the local deviations. And using just current volatility, the recent volatility, you can tell what to expect, right? What range of possible values you're going to see in, what are likely value to expect. So it's actually a pretty good way of visualizing Bitcoin behavior, and it has predictive value. Because if you have a big deviations from this trend, you will expect a correction. What is different from previous cycles right now, if you want to talk a little bit about the current market, is that we are following the power law, and that is okay for a little while, but then sooner or later we are supposed to leave, right, and start to see additional volatility, and we don't see that yet, and it's possible that it's just transitory, right, because it's kind of similar to these or these, right, this area. They usually don't last long, and then, right, we start to have this much more volatility that pushes the price up. Because it's not symmetric, right? It's kind of log normal. You have this tail towards large deviation, positive large deviations. So we will see if this is repeated, right? But this model also are useful to compare the present and the past, right? Okay, this is what happened in the past. Let's see what happened now. So far, it's all seems still okay, but yeah, we will see if previous past are repeated. Now, I have one more thing, and we can maybe start the discussion and continue the discussion next time. And this is a related but different topic. And hopefully I'm not too polemical with this topic, and sorry to involve you, but I wanted your opinion about this because we have used this model. I made calculations in this model. I'm talking about the quantile model. So I would like to discuss that for a moment. And I'm going to show you a graph that is relevant to that. And I already shared this graph with you, but let me explain it to our audience. And mostly we are doing this, at least from my side, I'm doing this because I do truly want to understand these models, right? And did you teach at any point, Stephen? Were you just a researcher at the university, or you were also?
No, only when I was a TA, for a very large lecture class, and then with some sections. But
you're a very good teacher, by the way. But I've been a physics professor for 9 years, and to me, the teaching component of this job, because this is my job right now, being interacting with the public, trying to talk about science, and in particular how it is applied to Bitcoin. It's a very important component for me, because it's not. I'm just trying to share my experience and my understanding of things, So, and that is part of what motivates me in going deeper in this kind of thing. So, the topic that we are discussing, and we can, like I said, we can spend a little bit of time and maybe revisit next episode, is what the different models tell us, right? What if, because basically the idea, this is how I see it with the power law. It's clear there is this power law behavior, it's real. There is some kind of scaling behavior. That is the main message that we get from the power law, that Bitcoin has followed these, the price of Bitcoin has followed this progression where as you change the price in terms of scale, so you go up 10, 100,000, you need more time to go to the next step, right? That the scale of time is proportional that is what a power law is, with the scale of a price, right? So by the time you go to the next scaling price, so you go from 100 to 1,000, well, you will require longer time, because it takes, you have to increase also the scale of time. It's not going to be any more days, it's not going to be any more weeks, it's going to be years. And in fact, right now we are talking about when we are going to reach 1 million, it's going to take a decade. It's not going to be in years anymore.
It's not just time, Giovanni, it's money.
Yeah.
You need more money.
You need more money.
Fiat
So
has to come into the system, right?
Right. But
Right.
exactly, right? So it's and this is why you see this scaling behavior, because you're scaling the money involved in the system. So that is really the core message. Now, the reason why we use the linear regression, right, and the least square regression, is because it's the simplest possible thing to do, right? We do it. It's simple. It has a simple interpretation. It does an okay job, and I think the okay job is due to exactly what we just showed today. We have this bimodal behavior, and so in a sense, you have a bunch of points above, a bunch of points below. They kind of cancel each other, and we just demonstrated, yes, maybe they are not the textbook example where you have basically a fuzzy, power law plus some scattered Gaussian noise. We don't, because life is much more complicated than that. But it's close enough, right? There are actually two Gaussian, or something that looks like a Gaussian. And so it's still working okay. The least square regression is not perfect, but it does an okay job. Now, you can go more sophisticated and say, can I use other type of regressions, right? Other type of it maybe do not imply a Gaussian distribution. And the quantile model, because it's kind of parametric, right? It's a parametric approach to regression, doesn't imply a precise distribution. But it's not true, like some people claim, like let's say, for example, it's not because we want to put on the spot somebody, but just to give a reference, right? And it's a debate, it's a discussion, right? We are trying to explore things together. So Plan C, for example, he makes these claims that is a model that is completely, doesn't make any assumption at all. It can handle any particular behavior, statistical behavior. And I don't agree on that. And I'm worried about overextending the interpretation of a model. And it has, like anything, it has strength and weaknesses, right? And we can discuss that. One of the things I want to illustrate, and I want to see what you think, right? It's this example. So I created an example, and being a physicist, you can confirm, right? Many times when we want to understand something in physics, we create what are called the toy models, that are very simplified version of something that we want to study. Like, for example, if we want to understand vibrations, we look at a spring. A spring, you will think that a spring is a very, very precise and particular object, and it's not something that has a universal value. But it turns out that little simple spring can represent a lot of type of vibrations that you can find everywhere, right? From how a star oscillates, organ expands or contracts. It's a spring, and you think that by focusing on the spring, you only learn about the spring, but actually you can extend whatever you learn about the spring to many, many systems, right? That is something that we do all the time in physics. So in this toy model, creating a power law, and I know the beauty of these and doing the toy models is that you have control of everything. You know what your input is. You created it, right? I created, for example, here a power law with a slope that is 5.8. So I know exactly the slope. I know all the parameters of my system, and I added to these oscillations that are periodic, right? Very periodic. It's actually a sine wave, and they are a decay. So I also know the decay of this system, and I can add noise. I can add additional noise. but I reduce noise. There is a little bit of noise, but I reduce noise mostly to show how clean the signal is. And then I apply the quantile regression. And similar to your graph, right? The graph, and we can maybe show it as a comparison. You made a graph before of the quantile model or quantile regression of Bitcoin, right? And you see these different slopes, right? Different is not the answer to the quantile. So the quantile does this calculation, and there is a process. We discussed it in one of the previous episodes, and it gives us an answer. And the answer is, I think there are a bunch of power laws, right? And in fact, in my algorithm, I have printed to screen all the different slopes. And I know that my value, my real value, because there is only one power law, is 5.8. And when I ask to print all the value of these different power laws, because you see, they are all straight line, right? These quantile levels in my example that are these color lines are the quantile, right? Starting from 0.5 going all the way to 0.95. There is a bunch of power laws. In fact, there are an infinite number of them, but here I'm representing just few. And the slopes of these guys, they go all the way from 5.1 to 6.5. So the question is, and then the next thing, so that is the first thing, right? What is the meaning of these different power laws? How come we get different power laws when we do the quantile model? And what should be the interpretation of them? And second, if you think that the quantile model helps you to predict where the next peaks are going to be, the result of this experiment shows that it doesn't do a good job with that, because notice how after the first few oscillations, like maybe 3 or 4, all the different oscillations go through different type of quantile. So if you were tempted to think that 95% quantile is where all the peaks are, after that is maybe true for the first few oscillation, but then it's not true, because you can see it doesn't really, the quantile regression really tell us where the next oscillation are going to be, because we are going across many different.
Couple questions.
Yeah. Yes.
Well, first of all, it looks like you used a period that's roughly half a year, maybe 200 days. Is that roughly it?
I shortened the period
because you're trying to bring out. Right? So just to put some context,
I could still use 4 years and then look at a longer period of time. Right. It will be.
So a few things are going on here. One is we have the core power law is 5.8, and then we've got these quantiles, and then we've got this damped periodic oscillation. Then a couple hundred days, and then what's the damping time scale here? It's, I don't know, a few years probably.
Yeah, a few years.
Yeah. Okay.
Yeah.
Or so that could apply, in this toy problem, or it could apply more generally to Bitcoin looking out over decades, right? So how would taking quantile approach serve us if we're trying to project out to 10 years from now and 20 years from now and potentially beyond? What I don't understand here is why the quantiles are not going through the data points as the sinusoids dampen.
Right, because there is you can see by eye that you could not fit a straight line through these peaks.
So they're forced.
It's basically it looks like a straight line originally, because anything looks a straight line originally, right? That is the entire thing behind calculus, right?
So let me simplify. What's happening here is that they start very well spread out, but because the oscillations are damped, they're forced to converge once we get out to the terminus. And right now, the terminus is actually the current age of Bitcoin in this toy problem, right?
Yeah, roughly. Exactly. Yeah.
Yeah. So, if you had shorter periodicity for the bubbles and you tried to model everything with quantiles, you would have found that you're grossly overestimating the chance of getting to a higher price level.
Correct.
Right? So
Yes.
this is the complaint, is that the higher quantile projections of 90, 95, 99% do not really reflect that probability as you project them forward. If the bubbles are decreasing in magnitude, in terms of, you know, their logarithmic magnitude, and as far as we know, they are, and they've done so monotonically, right?
Yeah.
Yeah.
And so my interpretation of this is, think about what we are asking to the quantile model. Right? We are saying, at least in this representation of a quantile regression, because of course maybe there are other ways of doing it. But if you start and you give it an input, and the input is the log of a days, from when Bitcoin was created, and then you give it the log of price, and then you're saying, okay, use the quantile algorithm and do a linear regression, right? Because you do need to give that information. I'm sure when you created your algorithm, this is what you say, right? Create the linear regressions that are not least squares, but following the quantile algorithm. And so the output will be what you ask. It will be a bunch of lines. It cannot be anything else, right? It will be a bunch of lines in the log plot. This is why they do look like lines. And so once you try to answer everything, like if you have a hammer, everything starts to look like nails, right? So the algorithm is trying to do its best to represent this very complex signal, but it cannot really be represented by a bunch of lines. It's something more complicated. And so it's trying to do its best. This is why this upper line, it goes kind of through the first stops, because anything can be linearized, right? If you look at a very short interval. But then after that, it doesn't do a good job, right? And this first oscillation kind of dominates. So this is why the blue line is so high. Now, you could still save these regressions, saying, well, what that gives us, these two blue bands, then represents kind of extremes, right? Something that you can kind of be sure that we are not going above that. So then in that case, then yes, there is some utility in that, right? You have like a kind of very, very strong upper limit that is very unlikely we are going above that, right? That could be a good interpretation, but it's not a good measure to know where we are going. They are an upper estimation, and as more time passes by, more oscillation we are getting farther and farther away from that upper estimation. So it kind of loses a little bit utility, right? Because if it is such a higher value that it's completely unlikely that we go there, then it's not that useful. But it shows that it's not the answer to everything, right? I've been doing a quantile regression, but in the presence of a complex signal, it does an okay job, but it's not really this universal tool that some people think it is, right? Do you agree with that interpretation? Or do you have
Yes,
you want to
yes.
push back on what I'm saying? Or?
Well, no. I mean, I certainly accept what you've presented here. It makes sense, and I think that the problem with the quantile is when it's positioned as being time agnostic.
Right.
It is not time agnostic. Bitcoin follows a path. It's path dependent. So it has a path and it has volatility. It's instead of the drunk in the random walk, it's the drunk in the random walk with the dog, right? On the leash. And the dog is pulling it back to the power law.
Yes.
And sometimes the dog gets excited, it sees something, and maybe that's when you have a bubble. I don't know.
True. Yeah, it's
But
a good analogy.
the leash is pulling you back to the power law, and you do not random walk from one side of the road to the other. You have to take one step after another. It's path dependent, right? You take one step after another. And
Right.
so, and you have some volatility around each step. You have a volatility day by day, and you have a volatility week by week. You have volatility month by month, right? And what we tend to do is we annualize the volatility. Yeah. So that's the effective annual volatility.
I understand the motivation, right? It's a noble motivation because basically the idea will be, well, wait a second, let me agree on the power law overall trend, but I don't want to get married to a precise idea about oscillations and when the peaks are, when the bottoms are. Let me see if I can use a statistical approach. The problem with a statistical approach is that it cannot represent dynamics, right? This is why kind of we use statistic as the last resort when you see chaos, when you see disorder, and there is not a precise behavior that maybe is periodic, or there is some kind of other dynamics that you can observe. Then you go with statistics, right? This is why, for example, we have Newtonian dynamics, and then we have statistical mechanics in physics, right? It's just like a last resort approach where at least you try to get some knowledge, but it's knowledge of what we don't know, right? It's like a compromise.
Economists are sorely lacking in physical foundation, and so they resort to statistics.
Exactly. But the problem with this is you can see from this demonstration, this is what I was trying to demonstrate with this example, that if you have a very strong dynamic, then the quantile approach, that is all statistics, will not be able to capture completely the dynamics. It will come up with some almost nonsensical answer after few oscillations, right? Tells you there is this power law decay, and there is not a power law decay. There is an exponential decay, and it's not able to capture it because it's not, a comprehensive tool. It doesn't do what statistics is not always the answer for everything, So it's useful. It gives us some insight, but it should be taken with a grain of salt. That like everything anyway. But don't. If you sell it as, okay, this is this universal tool that can handle any situation at all, I don't agree on that. I don't think it's the correct interpretation. And you seem to agree with me, right? I don't want to.
You don't land on the moon with statistics.
Correct, exactly. Yes. So anyway, I think we cover a lot of interesting topics. Let's see if we have some questions that we can
there was
answer.
One good question, I think, about some of the details of the TradingView slide indicator.
Okay.
And what the interpretation of the lines there.
So we can go very quickly through some of them. So we have this one that says Bitcoin is a circulatory system. Yeah, there are a lot of analogy, right? One of the things that actually made me explore the power law was when I heard this lecture from Jeffrey West, and he was talking about, he has a beautiful lecture that I suggest everybody. I'm going to type it in the chat. It's called The Surprising Math of Cities and Corporations. And you can look it up. You can do a search. And this was actually the beginning of my exploration of the power law. I heard this lecture, and I was so fascinated because I was familiar, of course, with power laws. In physics, we adore power law, maybe a little bit too much. I'm going to send you one day as a gift, Stephen, a shirt which says, I found it online. I bought a few. It says, I went to a physics conference and all what I got was a lousy power law. So we are a little bit too enamored with power laws, but they come up everywhere in the natural world. This is why. And I was familiar with that. I didn't realize that physicists started to explore human system like cities, and they found all these power laws there. So he was describing actually the city as kind of an organism where the streets were the circulatory system. So these analogies actually are meaningful. And then the communication system as the nervous system of a city, and he was describing all this power law. And I had this vision that Bitcoin was like that. And then after the listening, I went and started to download all the data, started to analyze. And this is when I found my first power law. I found a power law between transactions, volume, on-chain transaction volumes, and the price of Bitcoin. It was a power law. And then I found price and addresses and so on and so on. This was my start, right? So this analogy actually are not just, they are meaningful. They help us in understanding this phenomena. It's a real thing. And so, it's a good comment. It's the most beautiful model I ever seen. Which one was the one that you wanted to discuss?
There's a question from Simply Complex about, am I correct reading the black line in the red areas is the mean reversion in a bull market? Something like that. If you can bring that slide back up.
Sure.
Oh, this one, yeah.
Share screen. I'm going to share this. Sure. Yeah, this one. And the comment. Yeah. Am I correct reading the black line in the red areas, in the mean reversion in a bull market, and the black line in the green, the blue line? Yeah, so the blue line is the usual regression that we do, like the standard, the least square regression that is a compromise, but it does a decent job. Mostly, I think, because of this dual behavior, right? It's kind of in the middle, so it's of an average between the two, and you can see that it's kind of almost equally distant from the black lines, and the black lines are the relative averages over time. So the average eventually should show the power law. If a power law is the real behavior, the average should converge to the power law. And in fact, you see, they do, they are parallel to that blue line. And all what they did, the way I created this black line is simply doing a cumulative average. So basically, I'm summing all the deviations from the trend, and then I add to the deviation the trend itself. And I did it for all the data point below the power law, the mean power law, the blue line, and above the power law. So I go back and reconstruct all this data from the deviation, from these normalized deviations, right? So I have a formula that says price minus trend divided volatility, right? So you can reconstruct what the supposed average price is from the deviations. And this is what I get. I get the two black line. I was very surprised by them because they really show there are these two regimes, right? From just averaging the data, above and below. You have to separate them. And so, yes, that is the right interpretation, that is kind of a mean reversion of the two regimes, that the price tends to go back to that line in both cases. It's just that the difference in behavior for the bull market is you have a little bit more skewed distribution. It tends to have a longer tail for the data above the power law. This is why you have these large positive deviations. So it's not symmetric as the one below. The one below is much more symmetric. And the data from, I'm curious to see how this looks like with gold. We could do it also with gold.
Yeah.
I will try to do it with gold. And then, in fact, I can send you the Pine script and you can work on it yourself if you like, if you want to apply to gold. And then, there are these deviations that are more skewed for the upper values and more symmetric for the lower ones. But they kind of catch most of the behavior, because if you are too far in either direction, then there is a correction, right? It's like more symmetric for the one below, where we tend to go down to the support line, and so you have a negative deviation from the black green line, and you also can have deviation that are positive where we go too far. Stephen pointed out that it didn't happen often. Like you can really literally count, like it happened this cycle where I think this was mostly due to excitement due to the ETFs, right? And then people thought that maybe this will go forever. No, it didn't. It reached the power law, and we had a correction. We went back. We mean reverted. We went back to this mean. And then the other time it happened was this. We kind of asked several times what this was. Like, did we ever figure it out, Steve? What was this excitement? What was this?
That one? When is that?
No, the upper one, when we went above a
Is
power
that
law.
mid 2019?
This was July of July 19. Yes,
mid 2019.
Yeah. I don't remember.
Yeah, that was. I'm just thinking about the stock market. The stock market bubbled up, and then there was a liquidity crisis.
Yeah.
Towards the end of 2019.
Right.
So exactly. I think there was a liquidity effect there.
Yeah.
And then of course, COVID happened.
And then COVID happened, right? That kind of reset it almost. It was like a general reset to bring it down to the support line. And then it was too much of a correction on the other side. And we mean return right here. So when we are not supposed to be above a power law, you don't stay there for a long time. You go back. You go back to this region. It can happen. Right? I mean, here you have almost like a textbook example where we stay confined in that region, very, very confined. And you can see, right, the data really oscillated around this line, right? Every time we went too far, we went back. So yes, that is the right interpretation. It is cool, because it means actually the power law is much more precise than most people think when you divide it in two regimes. Yeah. Okay, maybe we can look at these. I think the power law represents human storing value network. However, some humans have two stories very lumpy, consensus changes. Yeah, right. There are all these. Once you start to see the overall picture, you can make sense of a lot of things. I think the beauty of the power law gives like a framework. It's not just some kind of fitting, that seems to work. It's actually a way of understanding Bitcoin, in a larger framework. It has philosophical implications. Okay, many comments, very interesting comments, but I'm trying to scroll. Tell me if there is anything that catches your attention. Simply Complex says that makes sense. Higher energy rises, lower energy sinks. What do you want to say about this?
Heat, higher energy, lower energy sinks. Well, getting back to the fluid analogy, you think about waves in the ocean, right? I mean, you've got a large still body of water, and you've got waves on top of that. And if the still body of water is not as deep, you can get higher waves in proportion as there's less support underneath. So you can think of these as kind of waves, and people talk about that in markets. Can you catch a wave and so forth? The trick is not riding the wave with too much leverage for too long.
Yes, it's fundamental.
Yeah, and lower energy sinks. I mean, sure, it's money and time are energy, and you're seeing money pumped in, fiat being pumped in, and so that is a form of energy. It's not as good a form. It's not as directly tied to energy the way Bitcoin is, but it still represents energy.
Anyway, so we are almost actually no almost we went beyond the 1 hour. Maybe we want to keep it within the 1 hour. I think it's a good time to cover a lot of topics, and I think we did it again. It was a very interesting, complex but meaningful conversation, right? So we can come back next week and cover some other topics. Do you want to make some concluding remarks?
No concluding remarks. I've enjoyed being on again with you.
Yeah,
and thank you everybody for listening.
Yeah, thank you so much, guys. See you next week then. Bye, everybody.